Hello. I made a boo-boo. I had to print out your medical physics packs in a right rush before the college closed down the other week, and I forgot to include the stuff on ultrasound. Don't fret, I can go through it here on a piece of paper. Right. The first of your medical physics questions looks like this. And that's what an ultrasound probe looks like. You need to know how it works. So, ultrasound, it is just sound of higher frequencies than are audible to the human ear. So, beyond 20,000 hertz. We need to know how to produce ultrasound for a start. And it's produced through something called the piezoelectric effect. Okay. Now, this bit here is a piezoelectric crystal. And either side of it, there are some electrodes. A bit like the place of a capacitor. And if we connect that to an alternating voltage, this crystal will vibrate at the same frequency as the power supply. So this is very much like a capacitor again. So you'd put the crystal in between the plates, AC power supply. This vibrates at a frequency the same as the power supply. You don't need to know how the piezoelectric effect works, but you need to know the name of it and that piezoelectric crystals display that effect. As this crystal vibrates, it makes the air around it vibrate, and that vibration through the air is sound. All we need is for your power supply to have a frequency above 20,000 hertz, and you're producing ultrasound. Lovely jubbly. Great, we can produce ultrasound. Now, how do we detect the ultrasound? Well, this effect, it works both ways. If you've got a crystal and you put it between some plates and you just put a voltmeter there, if you make the crystal vibrate, it produces an alternating voltage, which you could measure there. Again, through the piezoelectric effect. So, if we look at this probe, what we've got here is something like this. You've got the electrode supplying alternating potential difference to the piezoelectric crystal between those plates. And you do that as a pulse. So you send out a pulse of ultrasound. Off it goes. That will bounce off something, come back, make this vibrate to produce the alternating voltage that you record. So it's a bit like perhaps sonar. You send out pulses, boop, ping, comes back, you detect it. It's a bit like echolocation. Okay, so that's how you produce and detect ultrasound. There's a couple of bits here on this. You want an absorber block in your ultrasound probe so that any ultrasound produced going that way won't reflect off the casing of the probe itself and come back and be detected. We just want anything that's going into the body to perhaps bounce off various tissues and come back and be detected. So the other bits you need to know about ultrasound is the different types of scans. We've got an A scan, which stands for an amplitude scan. So what you're going to get there is something like this. Blip. You send out a pulse of ultrasound. Some time elapses, and some ultrasound comes back. So you could look at the time taken, that ultrasound that's been reflected back has perhaps bounced off some tissue in the body. That time is the time taken for the ultrasound to leave the probe, bounce off part of the body, and come back. And if you know the speed of the ultrasound in the tissue, you can just do speed, distance, time, making sure that's the time to go there and back, you can easily work out the distance into the body, the depth inside the body. That's an amplitude scan. So simple speed, distance, time measurements there. The other type of scan we have is a B scan, a brightness scan. And that's when you get something like a picture of a fetus. So a pregnancy scan, that's supposed to be a fetus curled up in the womb. I'm sure you know the sort of thing I mean. So they are actually just the main bits on ultrasound. There's not a huge amount to say about these different types of scan. Simple speed, distance, time calculations for amplitude scan, brightness scan. You can just produce an image. How do you produce ultrasound? Piezoelectric effect. You make a piezoelectric crystal vibrate by applying an alternating voltage over it. That will produce the ultrasound. The piezoelectric crystal can be made to vibrate by ultrasound to produce a voltage, and that's how we detect ultrasound. Other bits which are important. Ultrasound reflects off when there's a change in medium. So if we go from skin to fat, or fat to bone, or muscle to something else in the body, some ultrasound would be reflected. Ultrasound reflects off changes in acoustic impedance. So when we go from one material to another, if the acoustic impedance, which has the symbol Z, Z1, Z2, if the acoustic impedance is different, ultrasound will be reflected. Also, some ultrasound will pass into the next material. A bit like when we've looked at refraction. You'll always get some reflection, but some of your light may be refracted. Similar idea here. Ultrasound, it reflects off materials of different acoustic impedances. There'll always be some reflection. There's going to be some ultrasound transmitted into the next material. How much depends on the ratio of these two values. So how do we calculate acoustic impedance? Z equals rho C. The acoustic impedance of one material equals the density of that material multiplied by the speed of ultrasound in that material. Don't use the speed of light, the speed of ultrasound in that material. And that will be different for each material as well. Now, that's the equation that's in the data book. There is another equation which isn't in the data book, and you don't need to remember because it's given to you in the questions. This one. Z2 minus Z1 squared over Z2 plus Z1 all squared tells you R, which would be the reflection coefficient. That is the fraction of your ultrasound that would be reflected. The bigger the difference between these numbers, the bigger the proportion of ultrasound reflected. That's why when somebody does go for an ultrasound scan, that's their skin, they get really larped up with gel skin. And that's what we would call acoustic matching gel. It matches the acoustic impedance of the gel to the skin. So when you bung your ultrasound probe on there isn't loads of ultrasound reflected straight off the surface of the body. Without the gel, you'd be going from air to skin, and almost all of the ultrasound would be reflected. No good. We want it to go in the body so it can then reflect off things inside the body and come back, and then we can work out where those things are in the body. They're all the main points on ultrasound. Signing out.